guys. In this tutorial, we're drawing the shear force and bending moment diagrams for this simply supported beam. We've got a pin at A, a roller at B, a 4 kilonewton point load 1 meter from A, and a 2,800 newton meter applied moment 1 meter further along. The question asks for the shear force and bending moment right at the middle of the beam at 1.5 meters. So here's the strategy. First, we find the support reactions using overall equilibrium. Then we build the shear diagram, then the bending moment diagram, working segment by segment from left to right. Are you ready? Let's do it. Step 1, the support reactions. We replace the supports with unknown forces, Ra and Rb, both assumed upward. Now take moments about A, counterclockwise positive, and Rb, 3 meters from A. The 4 kilonewton load acts 1 meter from A, and here's a nice property of applied moments. The 2,800 newton meter moment goes straight into the equation as it is. It doesn't matter where it sits on the beam, a couple has the same moment about any point. So let's write it out. Sigma moment about A equals 0, counterclockwise positive. First, the reaction force Rb at 3 meters will give counterclockwise moment at A, so it is positive, Rb times 3. Then the load 4 kilonewtons at 1 meter will give clockwise moment at A, so it is minus 4 times 1. And lastly, we have this moment counterclockwise, so plus 2.8 equals 0. Rearranging, Rb equals 4 times 1 minus 2.8, all divided by 3. That's 1.2 divided by 3, which is 0.4 kilonewtons or 400 newtons. The next step is to access the vertical equilibrium, which means we only consider the vertical linear forces acting on the structure. So we have here Ra, Rb, and the load 4 kilonewtons. Anything going up is positive and going down negative. Then using vertical equilibrium, where sigma Fy equals 0, so Ra plus Rb minus 4 equals 0. We know Rb is 0.4, then Ra equals 4 minus 0.4, which is 3.6 kilonewtons. Both Ra and Rb came out positive, so both act upward as assumed. And notice the physical story here. A carries 9 times more load than B because the 4 kilonewton force sits much closer to A. The numbers already make sense before we've drawn anything. Step 2, the shear force diagram. The method is simple. Walk along the beam from left to right, and at any position X, the shear equals the sum of the vertical forces you've passed so far. What we will do is we are going to slice the beam segment by segment. We see that we have the first load here, so the first segment is from 0 to 1 meter, or from A up to just before the load. Let's draw the diagram. The only vertical force behind the cut is Ra. Now at the cut section, this is where we have the internal forces, which are the shear force and the bending moment. Remember the sign convention. At the right hand side, the shear will be pointing down and the moment will be counterclockwise. So for the shear force, we apply the vertical equilibrium where sigma Fy equals 0. We have Ra minus V of x equals 0. And from here, V of x equals Ra equals 3.6 kilonewtons. This equation means from 0 to 1 meter, the shear force is constant at 3.6 kilonewtons. Now let's draw this on the SFD diagram, and don't forget to put the unit kilonewton at y-axis and the unit meter at x-axis. Let's assume 3.6 kilonewtons is here. Then from 0 to 1 meter, the shear is constant at 3.6 kilonewtons. The next segment from 1 meter onwards, we can see the moment here. We can slide the beam up to just before this moment, but because the concentrated moment doesn't have effect to shear, we can pass through and slice it just before point B. So let's extend this diagram. First, this is from 1 to just before 3 meters. Let's put again the internal forces. And now we have the point load 4 kilonewtons here at 1 meter. Again with vertical equilibrium, sigma Fy equals 0. We have Ra minus 4 minus V of x equals 0. And thus V of x is 3.6 minus 4 equals negative 0.4 kilonewtons. Note that V of x here is only applicable for x from 1 to 3 meters. And that means from 1 to 3 meters, the shear force is negative 0.4 kilonewtons. So the first answer is done at mid-span, 1.5 meters, and the shear force is negative 400 newtons. Pay attention at the location of the point load here. The value just before the load is 3.6 kilonewtons, and just after, it drops to minus 0.4 kilonewtons. This is the jump at the discontinuity, but the total height here is 4 kilonewtons. This can be your built-in check that your calculations were right. Now we are done with the shear force diagram. The next step is step 3, the bending moment diagram. The key relationship is that the slope of the moment diagram equals the shear. Since our shear is constant on each segment, we can predict already that the moment will be a linear equation, or the diagram will be made of straight, increasing, or decreasing lines. And here, both supports are simple, so the moment is 0 at A and 0 at B. We are going to cut beam again as before. The first segment from 0 to just before the 4 kilonewtons load, we set that the net moments at A, counterclockwise positive, is 0. So M here is counterclockwise, so it is positive. V here times the lever of length x gives us clockwise moment at A, so it is minus V times x and equals 0. So we have M of x equals V times x, and we know that V at this segment is 3.6 kilonewtons, so this equals 3.6 times x, and the unit is kilonewtons meter. And we can see from this equation, if x equals 0, M is 0, and if x is 1, M is 3.6 kilonewtons meter. Let's put this on the bending moment diagram. Again, don't forget to put the unit at both x and y axis. It starts from 0, and at x equals to 1 meter, it goes linearly to 3.6. So this is our first graph for the first segment. Now for the second segment, we will go from 1 meter onward, but because we have the moment here, and our analysis is for the bending moment, we have to slice the beam just before this moment. So this is our diagram from 1 to just before 2 meters, and now we have the 4 kilonewtons load here at 1 meter. Again, sigma moment at A, counterclockwise positive, equals 0. We have M counterclockwise. V times the lever arm x clockwise at A, so minus V times x, and the 4 kilonewtons times the lever arm 1 meter, also clockwise at A, so minus 4 times 1 equals 0. Thus we have M of x equals V times x plus 4, which is negative 0.4 times x plus 4. So where is this minus 0.4 coming from? Again, we have to refer to the shear force diagram at the segment from 1 to 2 meter. The shear is minus 0.4 kilonewtons. Again, use the x here only for 1 to 2 meter. So for x equals to 1 meter, M is minus 0.4 plus 4 equals 3.6 kilonewtons meter. So we're going to start with the same value here at 3.6 at 1 meter. And for x equals to 2 meter, M is minus 0.4 times 2 plus 4, so equals 3.2 kilonewtons meter. So let's put these on our bending moment diagram. At 2 meters, it is 3.2 kilonewtons meter, so it is somewhere here. And so the graph will go down linearly from 3.6 to 3.2 kilonewtons meter. From this bending moment plot, we can obtain our second answer, which is at 1.5 meters. The moment is about here, in the middle of this line, which is in between 3.2 and 3.6 kilonewtons meter, which is 3.4 kilonewtons meter. But if you are not sure, then you use the equation, where for x equals 1.5 meters, the moment m is minus 0.4 times 1.5 plus 4 equals 3.4 kilonewtons meter. Now for the last segment, from 2 meters to just before point B, we now have the 2.8 kilonewtons meter moment here at 2 meters. Therefore, sigma moment about A equals 0 gives m minus v times x minus 4 times 1, and the moment here is clockwise, so plus 2.8 equals 0. And v at this last segment is still minus 0.4, so m of x equals negative 0.4 times x plus 1.2. So for x equals to 2 meters, m is minus 0.4 times 2 plus 1.2 equals 0.4 kilonewtons meter. So here at 2 meters, from 3.2 kilonewtons meter, the moment jumps down to 0.4 kilonewtons meter. Let's mark this value first here. And for x equals to 3 meters, m is minus 0.4 times 3 plus 1.2 equals 0. So the graph will go down from 0.4 to 0 at 3 meters. One last check, m at the roller is 0, and this is your second built-in check, and it confirms everything upstream. Again, notice the two values at the same locations here. This is the discontinuity jump, but the difference here is 3.2 minus 0.4, which is 2.8 kilonewtons, the value of the concentrated moment at this location. Alright guys, one design note before we finish. We can see here that the point force causes the jump in shear, and the concentrated moment causes the jump in moment. Next, instead of a point force, we are going to deal with a distribute force along the segment of the beam. Please subscribe, like, and share, and I'll see you again in the next video.